Traditional software engineering is rooted in deterministic logic. You write a rigid set of rules, the compiler executes them, and every time you provide the same input, the system produces the exact same result. This comparison shows how that logic breaks down in modern systems. On the left is the standard decision tree. On the right, an input enters a probabilistic model, triggering a cloud of statistical associations. Because the system uses learned representations, a single input generates multiple valid responses based on statistical weights. As of 2026, engineering roles have adapted to this variance. Applications now treat model inference as a primary layer of computation, integrated directly into the request-response cycle. Relying on prompt design alone cannot bridge the gap between a statistical guess and a production grade requirement. To build reliable software, you have to build systems that ground the model's reasoning. This is a raw, isolated large language model. Without an external architecture, it is functionally limited. It cannot access live company data, has no memory of prior interactions, and cannot verify its own accuracy. For an engineer, the objective is no longer focused on fine-tuning the model weights. The objective is architecting the environment that sits around the model. In production, that environment consists of 5 layers: context, retrieval, agents, evaluation, and deployment. By treating these as a unified stack, you create a system that can manage probabilistic outputs with the same rigor we once applied to deterministic code. If you ask a raw model to book a hotel for a specific conference, it may hallucinate the location. It lacks the situational awareness needed to distinguish between your company's travel policy and its own pre-trained patterns. Layer 1 is context engineering. As this diagram shows, we wrap the model node in blocks for state management and memory. This ensures the model operates within a specific set of operational boundaries and user-specific constraints. However, even a well-defined context is limited by the model's training cutoff. It cannot reason about events or data that didn't exist when its weights were last updated. We solve this with layer 2, Retrieval Augmented Generation, or RAG. This pipeline connects the model directly to a vector database containing your organization's live private data. When a query arrives, it shatters into a matrix of numeric vector arrays, allowing a mathematical search for relevance. The database returns a specific highlighted data chunk, which is injected back into the model's window, grounding the response and verified information. Engineers managing these pipelines must optimize for latency and manage the token overhead to ensure the retrieved data doesn't exceed the model's processing limits. Together, context and RAG provide the informational floor that allows a model to reason about real-world data in real time. Accuracy is only half the battle. In 2026, production systems are increasingly required to execute actions independently across different software tools. This is layer 3, AI agents. These systems use a continuous loop of perception, reasoning, and action to complete multi-step goals. Looking at the agent architecture, you can see how the RAG-enhanced model sends a signal to a planner. That planner breaks a goal into subtasks and uses a tool registry to trigger web searches, database queries, or external APIs. But an autonomous agent can enter infinite reasoning loops or trigger incorrect tool calls if its logic fails. Engineers prevent this by implementing strict framework boundaries and executing all agent actions within sandboxed environments. This architectural control ensures that when an agent acts, it does so within a verified safety layer. Because AI responses are probabilistic, you cannot use a standard unit test to confirm they are correct. There is no single binary pass-fail state for a generated paragraph. This makes layer 4, AI evaluation, a critical stage in the development lifecycle. Engineering teams in 2026 cite evaluation as their primary obstacle to deploying autonomous systems. This diagram shows the industry's standard LLM-as-a-Judge pipeline. A secondary, more capable model intercepts the agent's output and holds it in a sandbox for auditing. The judge node measures the output against specific metrics, factual consistency, tone, and relevance. It provides the automated score needed to block or approve a response before a user sees it. Without this automated scoring layer, there is no way to verify if a system update has improved the model's performance or introduced new hallucinations. You can build a functioning RAG system quickly, but scaling to handle thousands of concurrent requests often causes the entire architecture to fail. In layer 5 is deployment and scaling. In this environment, tokens are the primary unit of compute, and managing them is an infrastructure challenge. Engineers must solve for latency, how fast the model responds, and cost, as every generated token carries a specific financial price. This diagram illustrates hybrid routing to optimize costs. Incoming requests hit a router. Simple tasks are sent to small open-weight models, while complex reasoning is diverted to expensive commercial APIs. Real-time observability tools are used to track this routing, monitoring context window saturation, and token spend to keep the system financially sustainable. Deployment infrastructure determines whether an AI feature can transition from a successful prototype to a dependable production service. This unified 5-layer stack from context to deployment represents the current architectural standard for building autonomous AI systems. Industry data from 2026 indicates that 78% of AI engineering portfolios rely on generic tutorial-based projects. These portfolios typically result in less than 10 seconds of engagement from recruiters. To stand out, you must demonstrate end-to-end ownership, showing you can design the vector pipelines, the evaluation judges, and the deployment infrastructure that makes the system work at scale. Software engineering has evolved. Success now belongs to those who can bridge the gap between a raw probabilistic model and a rigorous production-grade architecture.